Hello, the second part of Smith charts is going to be single stub matching. As you can see, in single stub matching there is going to be four types: series stub, parallel stub, series open, short, parallel open, parallel short. Now I have written these numbers 0.25 and 0 near open and short for series, and in the reverse way for parallel stub. I'll explain that when we come to the Smith chart. Now consider this example. As we can see, it's a parallel stub and it is short. Now we need to do the parallel stub matching for the parallel short stub. So we go to the Smith chart. Now for stub matching, it's always easier if we thicken the z is equal to 1 or y is equal to 1 circle. As we can see, this circle you have to darken. Now if you have finished darkening, for parallel stub, open is at 0, short is at 0.25. So this is 0.0, so this is going to be open, and here you'll see 0.25, which is short. We have marked the open and short circuit. It's going to be much easier from now. Just come to the problem. The characteristic impedance is 40 ohms, the load impedance is 40 plus 80 ohms, 80 j ohms. So the normalized impedance is going to be load impedance divided by characteristic impedance, which in this case is going to be 1 plus 2j omega. So let's go ahead and mark 1 plus 2j omega on the map. As you very well know, this line is going to be the real part. This is where we're going to look for the imaginary part. So it's this circle, and as you can see 2 here. So this part is going to be 1 plus 2j omega. Now as you can see here, it's easier if you are working with YL for the parallel stub, and it's easier if you are working with ZL for the series stub. So draw the VSWR circle here and get to the load admittance point, which is YL. As you can see, we have drawn the line across from ZL through the center to the other point of the VSWR circle to get at YL. Now you have to mark the points where VSWR circle and the circle at this y is equal to or z is equal to 1 circle that we have darkened before. Here it's YB, and for YA it's going to be the same point, since that's the point where this circle touches this circle. So come to the circuit. As we can see, we need to find the distance from the load and length of the stub. So go back. Now take a look. We know the load, so we can go from load to generator, and it'd be much easier here. So come here, look at this wavelength towards generator. So this is the direction where we should travel. Let's find the distance from the load. Now as you can see, you have marked YL here, YA here, YB here. So let's find the distance of the stub from the load. So looking at this point outwards here, it is, as you can see, it's near 0.44. So let's take 0.44 and not 0.4 as I marked. It's actually 0.44. Okay, and look into these two solutions, YA, YB. The closest one would be YA, as we are moving towards the generator. So from this point it's closer to here than it's to YB. So consider YA and go and look towards what we are getting at YA. It is between 0.8 and 0.19, 0.18 and 0.19. So let's take it as 0.187. So we need to find the distance between 0.44 and 0.187. Now this whole chart has a length of 0.5, So let's consider this. 0.187 is going to be as it is. Now we need only this, and from here to here we need to discard. So 0.5 minus 0.44 will give us 0.06. All we need to do is add these values and we will get 0.193 lambda, which is going to be our distance, this one. So d1 is now 0.193 lambda. Now we shall find the length of the stub. So go back to the solution. Now this has an impedance part, imaginary impedance part of 2 here, as we can see the solution. So x is plus 2, so we will be using negative 2 to cancel this out. So as in graphs, the top part is positive, the bottom part of this chart is negative. Let's go here and find 2. So I have marked it here. As you can see, this is 0.2. Now draw a line from the center of the circle here, 1.0 to 2, and extend it outward. We have drawn a line from the center through this 2 here, which we are going to use to cancel this plus 2 part of the solution. So go ahead and see what is the length here, which it's between 0.32 and 0.33, and we are using the outermost part since we are moving towards the generator. As we can see here, towards the generator is going to be the outermost part, so be careful with this. Do not take 0.18 and 0.17. It's between 0.32 and 0.33, which is roughly here 0.324. Now this is a short circuit, so look at the chart again. We need to make it a short circuit. Short circuit is at 0.25, so 0.25, so the difference would be 470. So the length of the stub is going to be 0.074 lambda. 0 here, yeah. So this is going to be the length of the stub, and 0.193 is going to be the distance of the stub. So quick recap for single stub matching, and according to the sum we have a parallel short circuit stub, so we have to work with YL since it's easier for parallel stub, and 0.25 is going to be short, so mark 0.25 as short circuit here, mark 0 as open circuit here, go to the sum and let's start. Now the normalized impedance is going to be load impedance divided by characteristic impedance, which gives us 1 plus 2j, which we have marked here as you can see in the chart. 1 plus 2j, if it's minus 2j you have to go to the bottom, but this is plus 2j, so it's here. And thicken the y is equal to 1 circle before starting to do the problem, so that it's easier. Now take this as the radius and draw the VSWR circle. Draw a line through the center from the ZL through the center towards this circle. Where it touches is going to be YL, and since it's a parallel sum, YL is going to be much easier for us to work with. Note down the distance of YL. So it's at 0.44, if you can see, yeah, it's right here, 0.44, so 0.44. Now this is the closest part to this one, as we are going towards the generator, and towards the generator is going to be the outermost circle. So come here and look for the outermost circle. We have it between 0.18 and 0.19, which is 0.187 is what we are assuming. Now to find the distance between this, the whole length is 0.5, so we need just this part. So 0.5 minus 0.44 is 0.06, plus this part, which is 0.187, so 0.193 lambda. This is going to be the length of the, distance of the stub from the load here, d1, 0.193 lambda. And now the solution we have chosen where the 2 points intersect, this one, it actually has an imaginary impedance part x 2.0, yeah, here. Now we need to bring this down to short circuit here. So since this is plus 0.2, we will cancel it out using minus 0.2. The bottom part of the circle is minus, so go and choose 2, so minus 2. Draw a line from the center of the circle, extend it outwards. Now down the distance here, it's between 0.32 and 0.33, and it looks like it's at 0.324, which we have written down here. Now we need to bring this to short circuit. So as we have known from the beginning of the sum, 0.25 is the short circuit. So write it down and subtract, we get 0.074 lambda, which is going to be the length of the stub. So this d1 is going to be 0.193 lambda, and length of the stub L1 is going to be 0.074 lambda. Now this is for this example, which is a parallel shot, and the same way we can calculate it easily for an open parallel open stub. All you need to do is see, we have cancelled it out and brought it to short circuit, and for open we have to go towards the open circuit. That's the only difference we have to make for parallel open. And for the series stub, we have to work with ZL instead of YL. So instead of calculating the distance from here, we'll be calculating the distance from here, and initially we have to change this one open circuit. This is not open circuit anymore, this is actually the short circuit. This 0.0 here becomes short circuit here for series, and 0.25 becomes open. So we have to change this, and the only other changes, we have to change YL with ZL. So instead of calculating the distance from YL to the two solutions, we will be calculating it from ZL. That's the only difference we have to make for a single stub matching if it's series. And thank you.